21 years ago, 2 probes were launched on an unprecedented journey through the solar system, planning to visit at least 2 planets, with the second probe, Voyager 2, daring to continue on its path and visit 2 more, the outer ice giants of the cosmic neighborhood. It is a voyage as daring and bold as the first circumnavigations of our globe, and Voyager continues to contribute to mankind's legacy and his knowledge every day. August 1981. Voyager 2 flies by Saturn, the 6th planet in the solar system. It, alongside its sister probe Voyager 1, has now completed its primary mission, the exploration of the 5th and 6th planets of the solar system. Any further exploration attempted now is outside of the warranty of those who constructed the Voyager probes, and for a short while, it looks like Voyager 2 won't survive very long after Saturn. For a brief time, its camera platform was completely locked up, having temporarily depleted its onboard lubricant. But engineers on the ground are able to fix this problem, and Voyager 2 is given the green light to continue on its extended mission. After having visited Jupiter and Saturn, Voyager 2 will fly onward to Uranus and Neptune. It will be the only mission ever launched to attempt to visit these planets. Its sister probe, Voyager 1, has already departed on its own trajectory out of the solar system on a high inclination above the ecliptic. Voyager 2 now travels forward alone, our only hope at observing 2 new and unexplored worlds in our cosmic neighborhood. Uranus is the 7th planet from the Sun, and the first of the ice giants. Visible to the naked eye only as a small, faint blue dot, ancient humans considered Uranus to be nothing more than another star in the Milky Way. The ancient Greeks had listed Uranus among their massive star catalog. The French astronomer Pierre-Charles Lemonnier observed Uranus at least 12 times between 1750 and 1769. It wasn't until a period of time between the 13th of March and 26th of April, 1781, that English astronomer Sir William Herschel studied this blue point of light in detail. Herschel recorded in his journal that in the quartile near the constellation Taurus, he had observed a star and found that it is indeed a comet, for it has changed its place. When Herschel presented his discovery to the Royal Society, he continued to assert that he had found a comet. Although Herschel continued to describe his new object as a comet, other prominent astronomers of the day had already begun to suspect otherwise. Swedish astronomer Johann Lexell was the first to calculate the orbit of the new object. Its nearly circular orbit led him to a conclusion that it was in fact a planet, rather than a comet. This object was soon universally accepted as a new planet. In recognition of his achievement, King George III gave William Herschel an annual stipend of £200 on condition that he moved to Windsor so that the royal family could look through his telescopes. Agreements on the name of this new planet were not reached until 70 years after its discovery. Herschel himself decided to name the object George's Star, after his patron, King George III. Unsurprisingly, this name was not popular outside of England, and alternatives were quickly proposed. Swedish astronomer Erik Prosperin proposed the name Neptune. In March of 1782, Johann Bode proposed Uranus, the Latinized name of the Greek god of the sky. He noted the elegance of the name, in that just as Saturn was the father of Jupiter, the new planet should be named after the father of Saturn. Voyager 2 makes the closest pass to Uranus on January 24, 1986, only 2 days before the launch of Space Shuttle Challenger on the ill-fated STS-51L mission. Uranus orbits the Sun once every 84 years. Its average distance is 2 billion miles, or 20 times the distance between Earth and the Sun. It has the most eccentric orbit of any other planet, with its closest point being 150 million miles closer to the Sun than its furthest point. the Sun is 400 times dimmer from Uranus than it is from Earth. But that isn't the craziest thing about this remote world. The Uranian axis of rotation is tilted 90 degrees away from the plane of the ecliptic. This gives it seasonal changes unlike any other planet. In winter, Uranus's north pole faces completely away from the Sun, and it cartwheels around the solar system. In summer, its north pole faces directly at the Sun. Each pole gets 42 years of continuous sunlight, followed by 42 years of cold darkness. As Voyager speeds past the icy world, it makes more astonishing discoveries. Uranus is 14.5 times more massive than the Earth, but only 4 times bigger. This indicates that, unlike Jupiter and Saturn, Uranus has considerable density. Uranus is made primarily of various solid ices. The planet is about 60% water ice, frozen ammonia, and solid methane. The total mass of ice in Uranus's interior is unknown due to the imprecise nature of Voyager's rudimentary instruments. It is the only probe to have ever attempted to visit Uranus, and measurements from Earth are simply not possible. Hydrogen and helium, the 2 light gases that comprise Jupiter and Saturn, constitute only a small part of the total mass of Uranus. The remainder of the non-ice mass is accounted for by rocky material, possibly molten, at the very core of this planet. Uranus's core is half as large as the Earth, comprised of silicates and iron, and is about 8,500 degrees. The ice mantle on Uranus, however, is not entirely solid. At such extreme pressures, the majority of ices are squeezed into a supercritical fluid that seems to bend the very laws of physics. Distinct gases and liquid phases do not exist at such extreme pressures. This supercritical fluid can effuse through solids like a gas, and dissolve materials like a liquid. This water-ammonia ocean is extremely electrically conductive, and acts as a superconductor to power and amplify Uranus's magnetic field. The extreme pressure and temperature deep within Uranus may break up methane molecules, with the carbon atoms condensing into crystals of diamond that seep down through the mantle like slow-moving hailstones. Experiments at the Lawrence Livermore National Laboratory in California were able to exactly replicate the conditions found on Uranus, and discovered that the base of the mantle may comprise an ocean of liquid diamond, with floating bergs of solid diamonds on top. Since ice dominates over gases in the overall composition of Uranus, it is not classified as a gas giant, but rather an ice giant. Uranus's lowest temperature is minus 371.5 degrees Fahrenheit, only 49 degrees Kelvin, making it the coldest planet in the solar system. One hypothesis for the cause of this was that far in the ancient past, Uranus was hit by a very large, planet-sized impactor, which caused it to expel most of its primordial heat. This hard impact hypothesis is also used to explain the planet's axial tilt, although another theory is a possible role in the late heavy bombardment, a solar system event that details how Saturn, Uranus, and Neptune were all thrown out further from the Sun by gravitational disturbances from Jupiter, Uranus making such a close flyby to Jupiter that it seriously affected the planet's roll, causing such an inappropriate axial tilt. In visible light wavelengths, Uranus is remarkably unremarkable. It has a bland, pale appearance. Voyager 2 observes a total of only 10 thin and wispy high-altitude cloud features. An explanation for this pallor is that Uranus has a much lower temperature and therefore overall energy than any other planet, which is the primary factor behind weather systems. Uranus has 27 known moons, most of them asteroids, but 4 of them, Titania, Umbriel, Ariel, and Oberon, are noticeably larger. The Uranian satellite system is the least massive among those of the giant planets. The combined mass of all major moons of Uranus is less than half of that of Triton, the largest moon of Neptune. The largest moon of Uranus, Titania, has a radius of only 490 miles, less than half of that of our moon. Generally, Uranus's satellites are fairly dark. They are ice rock conglomerates that include ammonia ice and carbon dioxide ice. One of the most geologically interesting moons of Uranus is its moon Miranda, the smallest of the 5 innermost moons. Discovered on the 16th of February, 1948, Miranda is one of the only celestial bodies in the solar system not named within the pantheon of Greek and Roman gods. Miranda's namesake is from the character Miranda in The Tempest, a play written by William Shakespeare. Like the other moons of Uranus, Miranda orbits close to its equatorial plane. Because Uranus orbits the Sun on its side, this means Miranda's orbit is almost perpendicular to the ecliptic, the plane upon which all the other planets and moons in the solar system orbit, sharing Uranus's extreme seasonal cycle. Miranda is perhaps the smallest object in the solar system that is spherical. Voyager 2 makes close-up observations of Miranda using its onboard telescopic cameras, and is only able to observe the southern hemisphere. Miranda has an inner core of solid rock and an outer mantle of frozen ice. It boasts one of the most extreme and varied topographies of any object in the solar system, including an 8-mile-high cliff face and chevron-shaped tectonic features called coronae, not found on any other object in the cosmos. The origin and evolution of these features is not fully understood. 3 of these racetrack-like grooved structures are up to 120 miles wide and 12 miles deep. More than 60% of Miranda's composition is water ice. One theory on the formation of this odd moon is that a previous incarnation of Miranda was shattered by a massive impact, with the fragments reassembling and denser ones subsequently sinking to produce the current strange pattern. Another holds that Miranda and fellow Uranian moon Umbriel were interfering with each other's orbits, and this orbital resonance created extreme tidal heating within the core of Miranda, making it geologically active. As Voyager 2 moves away from Uranus, it observes that, like Jupiter and Saturn, the ice giant has a ring system of its own. Uranus's rings are composed of extremely dark particles which vary in size from micrometers to a fraction of a meter, finer than lunar dust. 13 distinct rings have been observed, and all are extremely young. The dynamics and distance from Uranus indicate that they did not form with the planet. The matter in the rings may have once been a part of a small moon or moons that were shattered by high-speed impacts. Uranus's magnetic field is another oddity. It is not aligned with the physical poles of its planet, and does not originate from its geometric center. The magnetic center of Uranus is shifted from the physical center of the planet towards the South Pole by as much as 1/3 of the planetary radius. This unique set of circumstances results, combined with the fact that the magnetic field is tilted 59 degrees away from the poles, in a corkscrew magnetotail that is completely unique to the Uranian system. Wind speeds on Uranus, despite its cold climate and lack of a complex weather system near the top of the atmosphere, can reach 560 miles per hour. All of these discoveries and countless more are made by Voyager 2 as it leaves the domain of Uranus as quickly as it had entered. Also provided by Voyager are the first ever detailed photographs of a planet that is so far from Earth and so dimly lit by the distant sun, a sun that is 2 billion miles away, that it was once considered to be just another part of the brilliant cosmos that comprise our night sky. The trans-Neptunian coast is one of deep hibernation for Voyager 2. To preserve the integrity of its electronics, and to conserve as much as possible its consumables, including reaction control system fuel, Voyager 2 sleeps through the 3 years it takes to reach Neptune after the Uranus flyby, save for a mid-course correction in 1987. Before the flyby, the chief project scientist, Ed Stone, and his staff members decided to also perform a close flyby of Triton by consuming extra onboard propellant, as Neptune would be the final stop for Voyager 2. It had no further objects to visit once it had passed this second ice giant. Telescopic study of Neptune, whether on purpose or accidental, was not the means through which Neptune was discovered. It is largely argued whether or not Neptune was perhaps observed by Galileo Galilei in 1612, and like Uranus was simply labeled as another fixed star. But it is certain that Neptune is the first and only planet to be predicted before it was observed. In 1821, Alexis Bouvard published astronomical tables of the orbit of Uranus, attempting to predict the seventh planet's path around the Sun. Subsequent observations made to check the accuracy of these tables revealed substantial deviations, leading Bouvard to hypothesize that an unknown celestial body was perturbing the orbit through gravitational interaction. In 1845, French mathematician Urbain Le Verrier developed his own calculations, predicting the precise location of the would-be celestial bogey, somewhere out there, deep in the solar system. Le Verrier urged famous astronomer Johann Gottfried Galle at the Berlin Observatory to search with the observatory's massive refractor. On the evening of the 23rd of September, 1846, the day Galle received the letter, he discovered Neptune to within 1 degree of where Le Verrier had predicted it to be. In the middle of the 19th century, an eighth planet of the solar system had been discovered by mankind. The demand for a mythological name seemed to be in keeping with the nomenclature of all the other planets, and soon, Neptune became the internationally accepted name. Neptune is 3 times larger than the Earth, and 17 times more massive. Its gravity at sea level, 14 psi, is just 1.1 times the surface gravity of Earth, making it very similar to the third planet from the Sun in gravitational respects. Neptune's internal structure resembles that of Uranus. This windy, royal blue planet has a hydrogen, helium, and methane upper atmosphere, constituting a deep blue color. Deeper down, it boasts a frozen mantle consisting of water, ammonia, and methane ices, followed by a core consisting of nickel and iron. As is customary in planetary science, the mantle is referred to as icy, despite the fact that it is a hot, dense fluid. The mantle consists of a layer of ionic water in which the water molecules break down into a soup of liquid hydrogen and oxygen. Deeper down, superionic water forms, in which the oxygen crystallizes and forms solid chunks, but the hydrogen floats around freely within the oxygen lattice. Like Uranus, Neptune's methane may decompose into diamond crystals that rain downwards at a depth of 7,000 miles. At high altitudes, Neptune's atmosphere is 80% hydrogen and 19% helium. Prominent amounts of methane also exist in pockets, giving Neptune its blue hue. Water vapor also exists, forming long, streaked clouds over the blue atmosphere below. Neptune, like Uranus, is extremely cold, though does have a high amount of heat still emanating from its inner core. The planet averages minus 328 degrees Fahrenheit, or negative 200 degrees Celsius. Storms are visible on Neptune as it has an active weather system. The Great Dark Spot, an anticyclonic storm system spanning 10,000 miles across, is discovered by Voyager 2. 5 years later, observations from the Hubble Space Telescope did not observe the Great Dark Spot, indicating that storms on Neptune are short-lived. These dark spots are a window into the deeper atmosphere below, as they are essentially holes in the cloud deck. Neptune has the strongest winds of any planet in the solar system, with dynamic storm systems creating winds capable of reaching speeds of almost 1,300 miles per hour, reaching supersonic flow. If one were to fly in the upper atmosphere of Neptune, cracks and booms would be common, though not caused by lightning. Instead, dense pockets of air, breaking the speed of sound at the outside edges of violent cyclones. Methane, ethane, and acetylene consistently bubbles up to the top of the Neptunian atmosphere from below and migrates to the planetary poles, sinking back down again after losing temperature. Neptune is an astonishing 2.7 billion miles away from the Sun and completes a single orbit every 164.79 years. On the 11th of July 2011, Neptune completed its first full orbit since its discovery in 1846. Neptune's day lasts 16 hours and 7 minutes, and a total of 4 rings exist around Neptune's equator. As it passes Neptune, Voyager 2 observes the largest moon, Triton. Triton was revealed to have a remarkably active geologic past, and for the first time in history, active geysers are observed on a celestial body other than the Earth. Triton, however, is not like any of the other moons of Neptune, or for that matter, any other moon in the solar system. Triton is the only large moon with a retrograde orbit, an orbit in the opposite direction of its planet's rotation. Because of its retrograde orbit and composition similar to Pluto, Triton is thought to have been a dwarf planet in the Kuiper Belt, captured by Neptune. Moons in retrograde orbits cannot form in the same region of the solar nebula as the planet in which they orbit, so Triton must have been captured from elsewhere. Triton has a surface of mostly frozen nitrogen, as well as a thin atmosphere that contains clouds of nitrogen ice. Triton is comprised of 35% water ice. Its surface is geologically active, and a complex geological history reveals intricate cryovolcanic and tectonic terrains. Part of its surface has geysers erupting nitrogen gas, contributing to a tenuous nitrogen atmosphere that is 70,000 times thinner than the atmosphere of Earth. Triton is not the only moon in the solar system with a retrograde orbit, but all the others are captured asteroids around Jupiter and Saturn. These moons are all much more distant from their planets as Triton is from Neptune, as well as being much smaller. Triton's orbit is completely out of sync with the orbit of Neptune. Its orbit is tilted 23 degrees south of the Neptunian equator. Triton is tidally locked to Neptune, and its orbit around Neptune has become a nearly perfect circle, with an eccentricity of almost 0. Tidal interactions cause Triton's orbit, which is already closer to Neptune than the Moon is to Earth, to decay. It is predicted that in 3.6 billion years, Triton will pass within Neptune's Roche limit, which will result in a collision with the atmosphere of Neptune, or the breakup of Triton, forming a brilliant ring system similar to that of Saturn's. Triton may have been captured by Neptune while the planet was migrating outward from the Sun, in an event related to the late heavy bombardment. With a diameter 5.5% that of Neptune, Triton is the largest moon relative to its planet in terms of diameter. There is enough rock in Triton's interior for radioactive decay to power convection in the mantle. This heat may be sufficient to maintain a global subsurface ocean. Triton is geologically active, and its subsurface processes are similar to those that produce volcanoes and rift valleys on Earth, but with water and ammonia as opposed to liquid rock. This is known as cryovolcanism. The vast majority of surface features on Triton are endogenic, the result of internal geological processes rather than external processes such as impacts. All of the active geysers observed by Voyager 2 are located close to the subsolar point. which indicates that heating from the sun, although very weak at Triton's great distance, plays a crucial role. The temperature difference between sunlight and darkness being a meager 4 degrees Kelvin, 7 degrees Fahrenheit. Each eruption of a geyser on Triton may last up to a year, driven by the sublimation or transformation from a solid to a gas of up to 100 million cubic meters of nitrogen. Dust may be deposited up to 150 miles downwind of these plumes in visible streaks. Between 1977 and the Voyager 2 flyby in 1989, Triton had shifted from a reddish-brown color, similar to Pluto, to a far paler, bluer hue, suggesting that nitrogen frost had covered older reddish material. Triton's western hemisphere consists of a strange series of fissures and depressions known as cantaloupe terrain. The origin for this topography is unknown. Voyager 2, just as it had for Uranus, makes countless new observations of and around Neptune, the 8th planet from the Sun. It photographs other, smaller Neptunian moons, and from July to September of 1989, Voyager 2 had discovered 6 new moons of Neptune previously unobserved. Because Neptune was the Roman god of the sea, Neptune's moons have been named after lesser sea gods. Once its planetary mission was over, Voyager 2 began its interstellar mission, which NASA is using to find out what the solar system is like beyond the magnetic field of our sun. Voyager continues to this day to transmit scientific data and pioneer new paths. As of right now, Voyager 2 is only the 3rd man-made object to reach over 100 times the distance between Earth and the Sun. Voyager 1 was first, followed by Pioneer 10. While Pioneer 10 and its sister probe Pioneer 11 have long ceased communication with the Earth, both Voyagers are performing well and still communicating. The spacecraft is not as far from the Sun as Voyager 1, which has already entered interstellar space. It will officially leave the solar system in 2020. Voyager 2 is not headed towards any particular star, and will simply become another rogue object orbiting the center of our galaxy, the Milky Way. In 40,000 years, it will pass 1.7 light-years from the star Ross 248, and if it remains undisturbed for another 300,000 years, it will pass within 4.3 light-years of Sirius, the North Star. The Voyager space probes lie beyond anything else we have ever accomplished as a species, humanity's permanent imprint on the universe. They will last longer than Homo sapiens, than the Earth itself, than even the solar system. For billions and billions of years, these two husks of circuitry and metal, nicknamed Voyager, will continue to do just that. Voyage out on an incredible journey across the stars, forever moving forward in the spirit of unbridled curiosity that has cultivated the essence of human exploration since the dawn of man. These have been the Voyagers.